This is a guided reading for section 6.5. For this guided reading, it's assumed that you understood section 6.4. If for some reason the lecture was not sufficient or you missed the lecture on section 6.4, you need to read 6.4 before continuing on. Okay, so let's go ahead and get started. So open up your book to page 159. And on 6.5, you'll see the conservation of mechanical energy. Now, most of you are going to remember a good chunk of this, I think. So I just want you to look at a couple pictures and talk about a couple things. And so all you'll really have to do is look at hopefully the sample problems that are in this section. Okay, so first of all, a couple things on conservation of mechanical energy. Take a look at the upper right of page 161. You'll see a picture there of a sled going down a twisty turn hill. One of the advantages of conservation of mechanical energy is that we don't have to worry about the angles. Okay, we can simply apply, if there's no air resistance or friction, we can simply apply the idea of that ME is conserved and not have to worry about angles of hills and forces and all that stuff. So sometimes it makes our life a lot easier. When you're doing conservation of mechanical energy problems, in this text they'll refer to ME as just E. That refers to the energy of the system, and if it's mechanical you can put ME and that's perfectly fine. In that picture you'll notice that at the bottom of that trip they say the potential energy is 0 joules. This is figure 6.17. As long as you call the lowest point in your problem a height of 0, your lowest point will always have 0 joules, and anywhere above that point will have potential energies that are positive. My preference when I do problems will always be to have the lowest point of my problem be a height of 0 so that I won't ever have to even worry about a negative potential energy. So we'll always be dealing with positive numbers for the actual values of KE and PE. Okay, so just walking quickly through this trip, the guy starts out at rest and he starts to go down this hill. So starting out there at the top, it's all PE because he has a height, but he's not moving initially, so no KE. So you'll see the 0 joules and the 600,000 joules to the left of that picture with the little red sled. And then partway down the trip, okay, the very next one, he has a height above the ground and he's moving, so he has both KE and PE. And so forth and so on until he gets to the bottom when he has a potential energy of 0 joules and it's all kinetic. If there's no friction or air resistance, then all of the potential energy will be converted into kinetic energy. As you can see, the 600,000 joules stays 600,000 joules. In fact, if you add up the two numbers in the middle, they also add up to 600,000 joules, hence the conservation part of this. And it really is that easy if there's no air resistance or friction. Okay, so take a look at example problem 8, and then come on back. As long as you understood example problem 8, I think you're okay and you don't need to read that section. The one other thing I would do is check your understanding 3 and actually check to see if you get it right to make sure you know when you can apply conservation mechanical energy, and that's the key thing. Once you can apply it, most of you will be okay. It's just knowing when you can and when you can't. So check your understanding 3 and then come on back. Once again, if you're okay with that, I think you're okay with conservation of mechanical energy. If you want to take a look at example problem 10, you can. It's another problem where mechanical energy is conserved and you find differences in heights instead of, you find the final velocity of a cart. You don't have to look at it if you're okay with those first two things. All right, so that was it for 6.5. I want you to also take a look at 6.6 now. And before you read, I want you to read all of 6.6, but before you read it, you might remember a problem in physics where there was a girl going down a sliding board and there was friction and air resistance. Okay, you had to allow for that. Okay, and they told you were able to figure out in that problem how much energy was, I'm putting this in quotes, air quotes, how much energy was lost to friction and air resistance. Okay, those non-conservative forces were doing work on the system. Okay, so there was energy leaving, mechanical energy leaving the system because of friction and air resistance, because of them doing negative work on it. So as a result of that, you found out that there were so many joules lost, or that you found out the difference in the mechanical energy was a negative value. Okay, that's because there is air resistance and friction. So take a look at example. Sorry for the interruption. Take a look at example problem 11. And notice that they're calculating the work done by non-conservative forces. When they do that, the non-conservative forces in this case are like friction and air resistance. They get a negative 4,400 joules. Okay, that means that the mechanical energy of the system went down by 4,400 joules. Well, if the mechanical energy of the system is going down, that energy has to show up somewhere. That's the whole temperature increase, internal energy, friction, air resistance, all those other types of energy, either outside of the system or different forms. So please walk through example problem 11 nice and slow, and then come on back. All right. Welcome back. You should also look at example problem 12, a case where they're using what they know about the work done by non-conservative forces to solve for something else. Okay. And remember that this is kind of like finding out how much energy is lost when you're talking about work done by non-conservative forces. You take the energy you end up at, subtract it from the energy you started at. Whatever you lost in the problem had to show up somewhere. Okay, that's the work being done by the non-conservative forces, friction, air resistance, etc. So take a look at example problem 12 and then come on back. Okay, it's very important that if 11 or 12 was unclear before you start in on the homework problems that deal with that, you need to talk to me, okay? And I'll walk you through them step by step. In 6.7, it's about power, and we've learned about, let me make an analogy here to velocity. You guys learned about displacement, and then you said, okay, well, let's figure out how quickly displacement changes, or displacement divided by time. That rate of change of displacement was velocity. The rate of change of velocity is acceleration. So power is one of those, rates, okay, one of those time rates of doing something. In this case, power is work over time. Now, in physics, it was just plug and chug, and here you have to understand a little bit more than that. And I like to think of it as you can have a change in kinetic energy. Okay, that is the work done. If the kinetic energy changes more quickly, okay, you could have the same change in kinetic energy, but if the change in kinetic energy happens more quickly in one case, that's a case where you have more power. Okay, so power is how quickly is kinetic energy changing, or, written another way, work divided by time. Okay, it's the time rate of doing work. Okay, so take a look at the definition there in the middle. Make sure you're familiar with the basic equation, and read that one quick paragraph there in 6.7, and then come on back. All right, welcome back. To reiterate, it should have been just that first paragraph before the definition, and then turn the page. You do not need to read the rest of that section, but what you do need to look at is equation 6.11 on the bottom of page 166. Okay, right above that, it says work over time equals Fs. In the text, they refer to S as the displacement. So as a reminder, work equals force times displacement. So I'm looking at the equation above 6.11. So W over T equals Fs over T. So they simply substituted in for work Fd or Fs divided by T. Well, what is S over T, or displacement over time? Displacement over time is velocity. So you can rewrite the equation for power as power equals force times velocity. That comes in handy on multiple choice problems, and it comes in handy even on free response questions. It's one you can remember or derive quickly. So if you're given a force and a velocity, you actually have power. Just keep that in mind, and remember that sometimes you have to substitute in and rewrite. Okay. All right, that was it for 6.7. 6.8, you do not need to read. In fact, there's some stuff that's wrong. They refer to when you're rubbing your hands together, they talk about heat, and it doesn't actually make any sense the way it's written. But really what 6.8 is about is letting you know that there's other forms of energy besides mechanical. We will get into those. We'll actually talk about E equals mc squared towards the end of the course, and we will certainly talk about internal energy when we're doing thermodynamics. So just be aware, not everything's mechanical. You guys know that. Skip 6.8. All right. 6.9. You can read if you would like. There is one thing you do need to look at, and if you have calculus, 6.9 will make perfect sense. If you don't have calculus, 6.9 is like a little intro into some of the ways people will, or you'll be thinking in calculus. You might want to read it out of curiosity. But on the bottom of the page, I want to draw your attention to the graph. Okay, on the bottom of page 168, and even though this is a force versus displacement graph with a curve, okay, you can still apply this to a regular old line, a graph with a straight line, which you are responsible for. So if you have a graph of force versus time, you actually, or excuse me, not time. Oh my. Check that. Force versus displacement. Okay. So on the bottom of page 168, I misspoke. Not force versus time. Force versus displacement. If you have a graph with a straight line, curves you're not responsible for, of a force versus displacement graph, think about it. What's the area under that curve? Force times displacement. FD is the work done. Okay, so on a force versus displacement graph, the area under the curve, as seen like in the shaded region, example problem 14, figure B, okay, that area under the curve is the amount of work done, okay, over that displacement. It's just F times D. Keep that in mind. That pops up sometimes. And as always, for graphs, just a quick review. Sometimes the area has meaning. Look at the units or look at what you're multiplying together. And if it's the slope, okay, do delta y over delta x, see what the units are if you recognize that, or actually plug in the values and see if you recognize that. So always, whenever you get a graph, think, what's the slope mean? What's the area mean? 6.10 is just an additional example problems. So if you're having trouble with the homework or you don't think there's enough practice in the homework, that kind of thing, you can go take a look at some additional sample problems. Or if you're reviewing for a free response quiz or test, looking over these sections at the ends of chapters where they just have lots of examples is a pretty good way to get ready for the tricks on a free response question. That was it for this guided reading. Thank you.